Vieta's formulae. So what I would like you to do is pause the video and then have a go at deducing these formulas here. If p of x is equal to a0 plus a1x plus a2x squared all the way up to an x to the power of n, and then by the fundamental theorem of algebra it has the linear factorization an times x minus r1 times x minus r2 all the way up to x minus rn, where some of the r1s and r2s may or may not be the same. They don't all have to be distinct. But the point is we can write it in this form with a product of n values, or a product of n linear factors that expand out to give us this thing, I should say. Anyway, given that, then we can find a link between the a0, a1, a2, an, and the r1, r2, all the way up to rn. Obviously, this an is just the same as that an. So for all the other coefficients, a0 all the way up to an minus 1, we can find a link between them and the roots, r1, r2, and rn. So pause the video and have a go at showing that they should be equal to these things here, which are Vieta's formulae. Alright, let's go through, one way to think about it together. The point is, we're taking this thing here, this linear factor form of the polynomial, and we're expanding it out to get this coefficient form of the polynomial. So when we expand this product of n linear factors out, we should get this. And so one way to think about it, obviously, in order to get x to the power of n, there's only one way to do that. We have to multiply this x, by the next x, and so on, and finally we're going to multiply by the last x. And there's no other combination when we're multiplying out. And so it has to be all the x's multiplied and nothing else, and then it just gets multiplied by the an. So that's going to give us the an x to the power of n term. Now let's look at the an minus 1 times x to the power of n minus 1 terms. So we want to find how to get this in terms of the Ri values. In order to have a power of x to the power of n, well, in order to have a power of n minus 1 of x, that means it needs to be n minus 1 x's all multiplied together. So for example, we can multiply this x, we can multiply this x, and then we can multiply all the x's, but not this x, so not that x. Which means when we're expanding this product of binomials, which is two terms in a bracket, everything needs to get multiplied by everything else once when we do this giant expansion. And so if we've multiplied all the x's by each other as we're going down the chain, this x by this x by the next x by the next x and so on and so forth, but then we get to the last one, we don't want it to be this x, so that means the only other possibility is that it's this rn. So one of the combinations which will get us x to the power of n minus 1 is going to be rn times x to the power of n minus 1. So that would be this rn and then all the other x's. Another combination would be if we were to take not this x here. So this x here, the next x wherever it is, the next x wherever it is, all the way down to the last x. So all these other x's, except for the first one, get multiplied together. But because it's a product of binomials, there needs to be one of each of the terms in the brackets multiplied by one of all the other terms in all the other brackets. So that means the last one is going to have to be this r1 here. And so in our expansion to go through this combination of products, another term would be r1 times x to the power of n minus 1. Because we have n minus 1 x's all multiplied together, and then they get multiplied by the r1 because we don't want to multiply them by the last x and get x to the power of n. And you could do the same thing with this R2. It's this R2 multiplied by this x, and also multiplied by the next x, and the next x, until finally the last x. So that's going to get us R2 to the times x to the power of n minus 1. And so you keep doing that until you've gone through all of the ri's. So the last one in this thing that I'm writing here would be r n minus 1 times x to the power of n minus 1. And then observe that when we're doing this big product of binomials, when we're expanding that set of binomials multiplied together, there is no other way to get an x to the power of n minus 1 term. And so when we add all these things together, it's going to be x to the power of n minus 1 times r1 plus r2 plus rn. And just to keep you on your toes, I deliberately, of course, made a mistake. So maybe you were sitting there, yelling at your screen, like, Mr. Castle, you're so stupid. I got something completely different to you. Why? Well, the answer is because I was kind of wrong. I forgot to include the negatives. So actually it's negative r1 times x times x times x all the way up to times x. So actually it should be a negative r1 times x to the n minus 1 plus negative r2 plus negative rn plus negative rn minus 1. You get the point. So actually they're all negatives. So you can just stick a negative at the front, and that fixes that. And then finally, when we do the full expansion, observe that this thing is being multiplied by an. So we get an times, negative an times r1 plus r2 plus dot 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 plus rn times x to the power of n minus 1, and there's no other combinations of x to the power of n minus 1, and so that should give us what I didn't write there, an minus 1 times x to the power of n minus 1, so that is an minus 1 x to the power of n minus 1, and then from there this should be true for every complex number x, and so we can divide both sides by negative an to arrive at the first of Vieta's formulae. Alright, just in case that point about binomials didn't quite land. So a binomial is two terms added together, or in this case subtracted together, however you want to write it. But the point is we got a product of n binomials here. And when you're multiplying binomials together, a plus b times c plus d times e plus f, for example, when you're multiplying binomials together, everything gets multiplied by everything else. So it's that one times that one times that one, plus that one times that one times that one, plus that one times that one times that one, plus that one times that one times that one. You get the idea. It cycles through everything, and then you would do the same with the b's. If you don't believe me, we can expand it out first. So let's do the a plus b times the c plus d first. So that's going to be a times c plus a times d. So we've done the a's first, and then plus b times c plus b times d. So that's just from the definition of multiplication, really. And so observe that everything's being multiplied by everything else in the first two sets of brackets. And then we just do the same thing again with the e and the f. So it's this one gets multiplied by e, and then this one gets multiplied by f. And then we just repeat for the rest of them. Alright, so bearing that in mind, let's take a look at the last one, which I think is pretty easy to get, because this is this one is the only constant term in our expansion, and multiplying through the the product of binomials, we're going to take the an times r1 times r2 times ... and then the last one is going to be times rn. That's the only way to get our constant term a0. Everything else is going to have at least x to the power of 1 in it. And so that means, since by the fundamental theorem of algebra this thing here is equal to this thing here, that means we must have a0 is equal to an times negative r1 times negative r2 times all the way up to negative rn, which is clearly equal to negative 1 to the power of n times an times r1, r2, all the way up to rn. And then finally, dividing both sides by negative 1 to the power of n times an gives us the required result here. By the way, 1 divided by negative 1 to the power of n is equal to negative 1 to the power of n. Okay, finally let's take a look at this middle one here, where we're looking for the an minus 2 divided by an2. We're looking to prove that that's equal to r1, r2 plus r1, r3 plus ... plus r1, rn, and then the rest of it r2, r3, r2, r4, so on and so forth. Now this an minus 2 would be the coefficient of x to the power of n minus 2. So there would be an minus 2 x to the power of n minus 2 in there somewhere. So given this expansion here, let's see how we can get x to the power of n minus 2. Well, the only way to do that is to multiply all the x's together down the binomials except for 2 of them. And so the other 2 must be Ri coefficients. Oh, sorry, Ri roots. So, for example, we could have negative r1 times negative r2, and then the rest of it would be all x's multiplied together. So that would be r1, r2, and then all of the rest of them are x's, x times x times x times x, till we get to the end, so that would be x to the power of n minus 2. Now we could do the same thing for r2 and r3. So we could go, oops, don't forget to include the negative. Could go negative r2 times negative r3, which would be in there somewhere. I guess I'll write the bracket like that. X minus r3. So negative r2 times negative r3, so that would be included in our product. And the first one we're not including r1 because we want x to the power of n minus 2. So we'll take the x from here. So it'd be x times negative r2 times negative r3, which is just r2 times r3. And then the rest of them are all x's as usual until finally we get to the last one, which is an x. So that would be positive r2, r3, x to the power of n minus 2. And then, yeah, the only way in order to get all of the combinations of multiples that give us n minus 2 x's all multiplied together, so it gives us x to the power of n minus 2, would be to select any pair of Ri values. So in total there's going to be n choose 2 of these combinations. Why is it n choose 2 and not np2? That's an important point. Once we've multiplied r1 by r2 and we've gone down that multiplication chain, we're not going to do r2 and then r1. So r1 times r2 times x times x times x times x until we're done. And then we don't have to go down that exact chain which contains r1 and r2 and the rest of them are x's again. So we're not going to have r2 and then r1 because we already took care of that. There's only one chain that contains r1 and r2 is the best way to say it, I think. And so in order to include all of the multiplication chains, you just do all of the ones that contain r1 first. So r1, r2, r1, r3, all the way down to R1, Rn. And we've already done everything that involves R1, so we don't need to revisit R1 again. So now let's do all the ones that involve R2, but not R1. So that'll be R2, R3, R2, R4, all the way down to R2, Rn. And so on and so forth. You keep doing that until finally you get to the very last chain, which is all of the chains that involve Rn minus 1 and none of the Ri's before n minus 1. And so Rn minus 1, Rn is the last term, if you're going to do it in that order. And so there are n choose 2 of these, and all of them, all of those multiplication chains result in a power of n minus 2 for the x's. Okay, so we've derived the three formulas written that are explicitly written here, but there's a ... And so this first formula takes care of the power of x to the n minus 1. The second formula takes care of the power x to the n minus 2. And if we want to look at the one that takes care of x to the power of n minus 3, well, the way to do that would be to look at all of the multiplication chains that contain any 3 of the Ri values. So any 3 Ri's multiplied together. There are going to be n choose 3 of them, and the first one could very easily be R1, R2, R3 times x to the power of n minus 3. And it's going to be negative, of course, because we're actually multiplying negative R1 times negative R2 times negative R3, so I guess I should put a negative there. And then the next one would be, so we could do R1, R2, R4. And keep going like that until we get to R1, R2, Rn. And then you could go R1, R3, R4, x to the n minus 3. And you continue along that way, and it becomes very, very complicated to write it in a general form like this as an extension activity. If you would like, you could come up with a way to write this in a generalized kind of form that ends with R n minus 2, R n minus 1, Rn. And so, yeah, that's Vieta's formulae. So we have a nice set of formula here that can tell us how an expanded, how do the coefficients of a polynomial relate to the roots of the equation of p of x equal to 0, because that's what these Ri terms are.